Assalamualaikum, salam sejahtera. We are from Group 3. I consist of Muhammad Afan, Muhammad Al-Hafiz, Muhammad Daniel Aikal, and myself, Muhammad RC bin Abdul. Okay, I will continue with the abstract. The purpose of this experiment was to investigate the link between torque, the angle of twice of a circular cross, and the material property, which is bending moment, when subjected to various loads. The equipment serves as a foundation and a short shaft. A base frame contains a clamp on one end and a ball bearing in a house, which is clamp block on the others, which a three-jaw chuck passing a clamp and a torsion head on the outside side of a short shaft in the bearing. A hanger rope with an effective diameter of 75 mm was looped around the torsion head. Specimen in the form of rod length were held in place by a fixed clamp and spinning chuck located 450 mm away. On a base that can be moved along the length of the specimen, an up-shaft scale of degrees was fixed. When a weight applied to the hanger cord, a pointer on a spring steel strip marked the rotation of the specimen. The information was gathered, and a graph of angle of twist versus torque was drawn. The rigidity modulus was calculated and compared to the theory. Based on the collected data and graph, a conclusion was reached. However, due to several flaws made during the experiment, our result may be differ from the theory. Okay, for the objective of the experiment is to study the property of material, which is bending moment, when subject to different load. Okay, for the introduction, when twisted, a torsion bar, rod, or a bar resists twisting and tends to return to its original position. A torsion bar is a long spring steel element in automobile with one end rigidly attached to the frame and the other end twisted by a lever attached to the axle. As a result, the vehicle has a spring action. Okay, I will pass to Hafiz to continue the presentation.
So hello everyone, I am Muhammad Al-Hafiz bin Muhammad Qasim. I am going to present about theory and methodology. So for the theory, when the bar is subjected to the torsion, it can be imagined that the bar is made of multiple individual discs that rotates relative to one another when the torque is being applied. Therefore, the distribution of shear strengths that were created by torsion within the circular shaft can be determined. Furthermore, this will show that shearing strength Y varies linearly with the distance from the center of the cross-section area. The changes in the angles created by both sides of the shaft can be measured to obtain shear stress Y by using the following formula, which is Y is equals to P times angle over L, where Y is the shearing stress, P the length from the center to any point in the circle of the shaft, angle of the twist, and L is the length of the shaft. Shearing strength occur at the surface of the shaft is the maximum shearing strength, where P is equal to C as illustrated in the figure below. Therefore, the angle of the twist and the maximum shearing stress Y max are related as follows, where Y max is equals to C times angle over L. C is the radius of the shaft. In the elastic wrench, the shearing strength and stress T is related by applying Hooke's law, as the stress produced is not exceeded anywhere within the shaft. The formula used is Y max is equals to T max over G, where it is also equals to TC over JG. Solving for angle of the twist by equating both right-hand side equation for maximum shear stress, Y max TC over J times G is equals to C times angle over L. So the angle of the twist is equals to T times L over J times G, where T is the torque exerted of the shaft L is the length of the shaft, J is the polar moment of inertia, and G is the modulus of rigidity.
Okay, my name is Muhammad Afan Nilubidi. So I will present for apparatus, data, and calculation. For apparatus, as we can see here, we have ruler, vernier caliper, 1 Newton and 5 Newton weight, spanner, angle cord, torsion bar testing machine, and three type of material that we use in this experiment, which are aluminum alloy, nylon rod, and steel rod.
So the next part is for the methodology or the procedure. The first step in this experiment is the aluminum alloy rod was clamped in position and load hanger was placed on the cord. Second, the rotation scale was set up 450 millimeter from the fixed clamp and its pointer was fixed to 0 before starts to read. Next, the twist of each specimen were recorded for every 5 Newton increments until it reached 40 Newton. The load were removed and the position of rotation scale together with the pointer changed over 200 millimeter from the clamp. The fifth step is the specimen was changed to steel rod and the procedures were repeated from 450 millimeters in length. And finally, the nylon rod was clamped in position and the twist for 200 and 450 millimeters were measured when the load of 5 Newton by increment 1 Newton was applied to torsion head. Then the load were removed and the occurring of full elastic recovery was recorded.
Table 1 shows that the data for aluminum alloy, where the torsion head effectiveness diameter is given 75 millimeter and the diameter of aluminum alloy is 6.31 millimeter. So the experiment is set up for hanger load 5 Newton up to 40 Newton, and then the angle of twist of rod is recorded over 400 millimeter and over 200 millimeter. And then after that, we can calculate the torque over 400 millimeter and the torque over 200 millimeter. To calculate the torque, we can use the formula of torque equals to R multiplied with F, whereby R is 75 divided by 2 and multiplied with 5 Newton. So we get the value of torque equals to 187.5 Newton millimeter. The same method is used to calculate for 10 Newton hanger load up to 40 Newton hanger load for torque over 400 millimeter and the torque over 200 millimeter. And then after we got the value of torque, the question asks to plot the graph of angle of twist versus torque. So as we can see here, there are two plotted graphs, which are blue line and the orange line, whereby the blue line is the data over the graph over 400 millimeter, and the orange graph is over 200 millimeter, and the slope for over 400 millimeter is 0.009x, and the slope value over 200 millimeter is equal to 0.0049. Then we can proceed to calculate the modulus of rigidity over 200 millimeter and over 400 millimeter. To calculate the modulus of rigidity, we can use the formula G equals to L divided by slope times with J, whereby J is equals to pi multiplied with diameter of aluminum alloy divided by 2 to the power of 4, and we divided by 2, then we got the value of J equals to 155.74 millimeter to the power of 4. So by having the value of J, we can directly calculate the value of G for 400 millimeter and 200 millimeter. To for the G value for 400 millimeter, we take 400 divided with 0.0098x, multiply with 155.64, and multiply with 180 over pi. So the G for 400 millimeter is equals to 15025.72 Newton over millimeter to the power of 4. For the modulus of rigidity for 200 millimeter, we just apply the same formula and just replace the value of L with 200. Then we got the value of rigidity equals to 15025.72 Newton over millimeter to the power of 4. And then we can calculate the average of rigidity by take the value of rigidity over 400 plus with rigidity over 200 and divided by 2, and then we got the average rigidity equals to 15025.72 Newton per millimeter to the power of 4. And this table is for data for alloy rod, whereby the torsion head effectiveness is still the same, which is 75 millimeter, and the diameter of alloy rod is 4.99. Diameter of steel rod equals to 4.99 millimeter. This experiment is set up for 5 Newton up to 40 Newton, and then we recorded the data, the degree of twist over 400 millimeter only, and then we can calculate the value of top over 400 millimeter. So to calculate the value of top, it just same goes to the data 1, where top equals to R multiply with F. Our value of F is 5 Newton time with 75 divided by 2. Then we got the top value equals to 187.5 Newton millimeter. So the calculation is repeated for 10 Newton hanger load up to 40 Newton hanger load. And then we should plot the graph of angle of twist versus top. So this is the graph for angle of twist of steel rod versus top values, and the value of slope is equals to 0.010606. So by having the value of slope, we can directly calculate the modulus of rigidity by applying the formula G equals to L over M time with J, where J is equals to pi multiply with the diameter of steel rod divided by 2 to the power of 4 divided by 2. So we got J equals to 60.87 millimeter to the power of 4. So the value of J obtained, we substitute in the formula of rigidity. Then we got the value of rigidity equals to G equals to 35520.04 Newton per millimeter to the power of 4. Okay, next is the data for data 3, which is for nylon rod. So the torsion head effectiveness diameter is 70 millimeter, which is same goes to data 1 and data 2 just now. And the diameter of nylon rod is 6.525 millimeter. So the experiment is set up for 1 Newton hanger load up to 0 Newton hanger load. And then we record the angle of twist of rod over 400 millimeter and over 200 millimeter. And after that, we can proceed to calculate top over 400 millimeter twist and 200 millimeter twist. So the step of calculation of top is just same as the data 1 and data 2 just now, where we use the formula of R multiplied with F, where our R is 75 divided by 2 multiplied with 1 Newton. So we got the value of torque equal to 37.5 Newton millimeter. So the same method is repeated for 2 Newton hanger load up to 0 Newton hanger load. And we were required to plot the graph, and this is as you can see the graph of angle of twist versus torque, where the blue color is the graph of 400 millimeter twist, and the orange color is graph of 200 millimeter twist, where the slope of 400 is 0.0363 and the slope of 200 is 0.0178 slope. And then we need to calculate the modulus of rigidity by using the formula of G equals to L divided with slope times with J, whereby our J is equals to pi multiplied with the diameter of nylon rod divided by 2 to the power of 4 and divided by 2 again, and then we got J equals to 177.96 millimeter to the power of 4. When we got the value of J, so we can insert the J in the rigidity formula. For 400, we take 400 divided by 0.0363 multiplied with 177.96 multiplied with 180 divided with pi. So we got the rigidity equals to 3547.75 Newton per millimeter to the power of 4. Same goes to 200 millimeter twist by replacing 200 divided by 0.0178 multiplied with 177.69 multiplied with 180 divided by pi. So we got the value of G equals to 3617.51 Newton per millimeter to the power of 4. And then we need to calculate the average of velocity, average of modulus rigidity over 400 twists and 200 twists by taking the value we calculate just now and divided by 2, and we get the value of average rigidity equals to 3582.63 Newton millimeter to the power of 4.
Hello there, my name is Muhammad Del Haikal, A1980-0124. We'll be explaining about discussion and the conclusion part. So there's actually two things that we need to actually discuss. That is, first one would be, to what extent does the experiment verify the torque twist formula based on the graph plotted, which was explained in the results part. So according to the three graphs that were plotted, it is concluded that the angle of twist is actually directly proportional to the torque. This means as the torque increases, the angle of twist also increases as well. Aside from that, the length of the rod or rod of material, which also affects the slope of the graph. This can actually be seen in graph 1, which is with aluminium rod, and graph 3 for nylon rod. When the length L is actually decreased, it will cause the slope to be steeper. The graph shows that the type of material will actually affect the angle of twisting and exhibit their purely elastic behavior. From the graph, the modulus of rigidity is inversely proportional to the angle of twist, which means that a smaller angle of twist will actually cause the value of modulus of rigidity, which is G, to actually increase as well. So in a nutshell, this actually means phi direct proportional to torque T, then phi is actually directly proportional to L, and phi is directly inversely proportional to 1 over G. So that means that the formula that was used to calculate the modulus of rigidity, G, is actually angle of twist equals to T times L over J times G, where J is the polar moment of inertia. So next slide. So the next one. So the next one would be the next part will be determining the modulus of rigidity G of materials. So from the table we can see that the aluminium rod from the experiment we can obtain is going to be 15,025.72 Newton millimeter per second, Newton millimeter squared. Steel rod would be 35,520.24, and nylon rod would be 15,645.06. The theoretical for the following 26,200. Steel rod would be 79,000 and 75,000 for nylon rod. So next slide. So actually from the table we can see that the difference between the theoretical and experimental values. The error for the rods are from 42% and the last one would be 79%. Among the three rods, we could actually see that the modulus of rigidity for steel is the highest. This means that it is the strongest material among the other two materials, and it is able to withstand higher shear stress and applied torque. Nylon has the lowest value for G, meaning it has the lowest ductility. So from the percentage error that we've gotten, it's actually greater than 20%, meaning that we cannot rely it entirely. So maybe there's some actually errors, and why and how to actually commit. So first one will be experimental error. The rod was not actually kept in good condition, causing the rod to be exposed to extra heat, making the temperature to rise unnecessarily and causing the error in the ductility. To make sure this does not happen, it will need to be kept in a place without extra heating or any hot place. So second one will be the systematic error. So parallax in reading the meter scale while taking the angle of twist value. This is quite easy. Make sure our eyes are actually just perpendicular with the meter scale while recording the value. So last one would be is the external error. So this is just random error, which means that environment that we've done in the environment, it was actually kind of windy or any flowing in the lab. This actually causes the weight to move, making the value taken to be inaccurate at the meter scale. So we need to make sure that when we do this experiment, it would be in a place that doesn't have any air flowing in the rooms. So next slide. So last part would be conclusion. So what do we get from the experiment actually? So actually the experimental values that we obtain varies greatly from the theoretical value. This is maybe due to the errors that occurred during the experiment. Some may be being avoidable and some are not. Other than that, the formula of torque was not satisfied. Well, due to the huge difference that we've seen, which is the percentage error from 42% to 79% between the theoretical and experimental value. Aside those, a conclusion can actually be made from the graphs plotted in results, which in conclusion, the greater the torque, the greater the specific material's angle of twist. So below are the modulus of rigidity G of the materials that we have calculated from the experiment. So I think that's all for our part. Experiment 6. Thank you.